Good evening. In the last session, we had discussed various mechanisms for implementing the spin locks when multiple threads needs to access a shared resource or critical section concurrently. And we looked at four different algorithms. In particular, Peterson lock, test and set lock, test and set lock, and exponential backoff lock. Right. So just I'll recap the previous logs. So initially we discussed about Peterson lock. So Peterson lock uses two Boolean flags for one for each thread and an integer variable which represents the victim. So here flag is set to true when a thread wants to enter into the critical section, and it sets the victim to the other thread IDs. And the main problem with the Peterson lock is it will work for only two threads. If we want to work with multiple threads, it's not possible by using the Peterson lock, right? So in order to overcome that problem, we are going with the test and set lock. So in test and set lock, so multiple threads are trying to contend for a lock. So whenever these three threads are trying to acquire the lock, so these three threads will spin on this particular variable is trying to perform the get and set operation or test and set instruction. So only one thread will succeed. That particular thread will enter into the critical section, right? And after that, whatever the remaining threads are there, remaining threads will keep on spinning on that particular locked variable. So which causes the contention. So to avoid that particular problem, we are going with the concept of test and set lock, test and set lock, right? So here, what is the advantage with this particular lock is, so instead of continuously spinning on a lock variable, these threads first reads the lock variable status. Once the lock is available, then all these threads are trying to perform the get and set operation on this particular variable. So when compared to the task lock, in T-task lock, whatever the contention is, the contention is reduced. But whenever the lock is available, then all the threads are trying to perform get and set operation on that particular time, on that particular variable at a time, which causes the contention. So to avoid that particular problem, we are going with the concept of exponential backoff. So in exponential backoff, what we are doing is, so if a particular thread is failed in acquiring the lock, we will make that particular thread wait for random amount of time. Again, after that, it will retry to enter into the, try to get the lock. And if subsequent failures happen, then we are doubles the expected wait. This is what the exponential backoff. But in exponential backoff, we are having some problems. Like one of the main problem is we need to tune the parameters according to the mission, particular mission. Means if you are, and it is not portable across all the platforms, right? So these are the main problems with the previous locks. So, and one of the main problem with all these locks is these locks are not providing fairness. Fairness in the sense, whichever thread comes first, that particular thread should enter into the critical section, right? So these locks are not following the fairness. So in order to avoid that particular problem and contention problem, all these, we are going with the new locks called Q locks. So what is Q lock idea is? So it is simple. So we are maintaining a one queue. So whatever the weight threads are there, right? So in order to overcome the fairness problem, all those things in the task, T-task, and exponential backoff, we are maintaining the threads in a queue. So Q locks are a type of lock that allows threads to wait in FIFO order. FIFO in the sense first in, first out order. So for a shared resource, so in a queue, like here we are maintaining the queue. So in a queue, each thread can learn if its turn has arrived by checking whether its predecessor has been served or not. So if the predecessor is served, then it will it will pass the lock to the next thread. So here we are avoiding the unless useless invalidations or contention by keeping the threads in a queue, and each thread will notify the next thread in the queue. And here no need to bother about all other threads. That is the idea. So based on this idea, we are going with the concept of Anderson queue lock. So sometimes we can also call it as a lock, Anderson lock, or array lock. So simply sometimes we can also call it as array-based queue lock. So the threads shared an atomic integer field. So we are initializing with the 0. To acquire the lock, each thread automatically increments the tail field. Like if you look at this particular example, now whatever the next field is there, next field will point to the starting position, that is 0th position. So means in whatever the next field is there, we are initializing with the 0, index of this particular array, 0. And whatever the first field is there, always we are initializing with the true, means whichever thread comes first, that particular thread directly enters into the critical section. Now, so initially this particular thread is idle. Now it wants to acquire the lock. So how it will acquire the lock? So to acquire the lock, each thread automatically increments the tail field, or here we are using the next field. So automatically each thread automatically increments the tail field. So here for that purpose, we are using the get and increment. So this get and increment is an atomic operation. So it will return the next field previous value, and it will increment it to the next value. So here next field is updating the, if we are incrementing it, means now this particular thread will spin on this particular field. Okay, so here whatever the next is there, next is a atomic field, atomic integer field. So what it will do means it will use the get and an increment function. So get and increment means it will get the previous value, and after that it will increment the pointer to the next position. Means initially next is pointing to the 0th field. Now it is incremented to first field, right? So now this particular thread acquired the lock. After that, now the second thread comes. Now this particular red thread wants to acquire the lock. So in order to acquire the lock, what it will do means again it will call the get and increment function. Now get and increment will get the next value here. Next is the next field value, and after that it will increment it to the next value. Now it is calling the get and increment. After that it is pointing to the next position. After that, this particular variable will spin on this particular field. Now first thread is spinning on the 0th index, that is true, flag value is true, and second red thread is spinning on the second field, that is index is 1, and its flag value is false. Next, whenever this particular pink thread completes its operation, critical section operation, it will release the lock by updating the next field value to true. Now, so this particular field, this particular thread is released the lock, and it is indicated with the F, and it passing the lock to the next thread by changing its field to the true. Now, if you look at the task lock, T-task or exponential backoff, all the threads are spinning on a single variable, right? Which causes the contention. But here, each thread is spinning on a different location, right? So first thread will spin on this particular 0th index, and second thread will spin on second index. Similarly, nth thread will spin on the nth index. So here we are reducing the contention. So which leads to we are minimizing the cache invalidations also. Next, this particular thread is acquired the lock. Now, so here for implementing this particular lock under some Q lock, here we are using the Boolean flags. So first thread will be indicated with true, and the remaining threads flags will be indicated with the false. Next, here we are using the atomic integer. So atomic integer is next. So initially we are initializing the next value with 0. And this is the atomic operation. Only one thread can update at a time. And here we are using the thread local variable, that is my slot. So this my slot used to represent the index of that particular array. Next. So this is a one flag for thread, and this is the next flag value, and this is thread local variable. Now, so this is the lock and unlock algorithm of a Anderson Q lock. So here what will happen means, first, whenever thread wants to acquire the lock, first claim a slot by incrementing the next field. Means here what will happen means, my slot equals to next dot get an increment. So initially we are initializing the next value with 0. So 0 means next value will return the 0 to my slot. In my slot, it will store the 0 and get an increment. First, it will get the next value that will be stored in the my slot. And after that, it will increment the next value by 1. So here, initially, if you look at this one, next is pointing to the 0th position. So whenever we are performing this particular operation, then what will happen means this next pointer will simply point to the next location. So here it is pointing to the next location. Next, while not of flags my slot modulus n. So here what we are doing means, so this is a represents a busy wait loop. Means wait until the predecessor has released the lock. So it will keep on spin on this particular block of, this is called wait loop. So here, for example, for the first thread, it directly enters into the critical section. For the next thread it is false. Now my slot modulus n is it will be pointing to the first one, first index. In first index, flag value is false, not of false is true. So it will continuously spins until the predecessor node updates this particular flag bit to true. Until that time, it will be spinning on this particular while loop. This is called wait loop. After that, if any thread wants to release the lock, before that, it will change the my slot modulus n. I mean, that particular thread index to false. Why? Because some other thread can come and reuse it. So for that purpose, we are resetting that. Now, how to pass the lock to the next thread. So here, in order to pass the lock to the next thread, simply we need to update the my slot to true, right? So that we are doing here. So previously, if you look at here, so here means, I mean, in flags, when index is 1, the flag value is f, right? So we need to change it to true in order to pass the lock to the red thread, right? So my slot plus 1. So initially my slot is at 0th position. So 0 plus 1, 1, modulus is 1. So flag of 1 is changed to true. Now it means this particular thread will acquire the lock, right? Simple. Now, so when compared to the remaining locks, so it is a straightforward one. So here it minimizes the contention also. Now, here we are saying that it is spinning on a local variable. Is spinning really local if multiple threads bits sit in the same cache line? So what is cache line means? So cache memory is organized into cache lines. Okay. A cache line is the smallest unit of data that can be transferred between the main memory and cache, right? So what will happen means, here if all these bits are sitting on it, if all the bits are sitting on a same cache line, now what will happen means, for example, this particular line 1 shares the 4 threads and line 2 shares the 4 threads. If all these 4 bits shares this particular line, then on this cache line, if all the threads are performing the invalidations, then it will cause the contention, right? So here it is causing the contention. So to avoid this particular problem, we are going with the concept of padding. So what padding so which will cause the fault sharing, or we can say that a result is contention. So in order to avoid that particular problem, what we are doing is we are going with the concept of padding. So to avoid the fault sharing, each bit sits in a separate cache line, means only one cache line used for only for one particular thread. So other threads will be placed in the next lines. So this will reduce the contention on the cache line. Okay, right. So is it clear? Is there any doubts? Okay.
Here, sir.
Okay, right. Thank you. Right. So now what are the advantage with this particular Anderson Q lock or A lock? Now, the main advantage with this is it is truly scalable. So scalable in the sense, whenever we are increasing the number of threads, you will get the better throughput. As we increase the number of threads, you will see a increment in the throughput. But when it comes to the previous locks, you won't find that that much improvement. Why? Because so it will cause the contention. But here we are reducing the contention completely. And one more advantage is it is simple and easy to implement, but it is having several disadvantages. So the main disadvantage is if you look at this particular flags, so if I'm using 20 threads, then I need to create the flags with array of 20, right? So means, so it is not space efficient, means it requires knowing a bound n on the maximum number of concurrent threads, and it allocates the array of that particular size. So that is the main disadvantage here. So means if I'm using 20 threads, then I need to create an array with the 20 threads. If I want to use the 96 threads, then I need to create an array with the 96 flag bits. So this is a this is not a space efficient one. That is the main problem with this Anderson lock. Means one is space hog and one more is, so we are allocating, in order to avoid the contention on cache lines, we are allocating 1 bit per thread, means 1 cache line per thread. So that is the main problem. And one more is, if I want to use this particular Anderson lock, I should know what is the maximum number of threads I want to run. So that is the main thing. So if I don't know the number of threads, it's not possible to implement the Anderson Q lock. So I should know the total number of threads ahead. And if the small number of contenders are there, so at that time, it will what will happen? So if I'm having small number of contenders, then we can use the task lock or T-task lock. So that is also one more problem. Now, so right, this is the concept of task lock. So we'll see the execution part, then we'll go to the next lock. So here we are using the my slot index is equal to new, it is a thread local variable. So I'm declaring the thread local integer. Next, I'm initializing the value with the 0, like whatever the integer value is there, that is 0 initially. Then I'm creating the flag. So here for this particular array, so here I'm creating a constructor, like for this particular lock, I'm creating a constructor a lock. So here we need to pass the capacity. Capacity indicates the total number of threads, right? So size is equal to capacity, and I'm initializing the tail pointer with the 0. And flag value is also I'm initializing with the capacity, total number of, based on the total number of threads. And initially, whatever the flag bit is there, we are indicating, initializing the flag bit with the 0. All right. Next. Now, how to acquire the lock? So to acquire the lock, what I'm doing is my int slot equals to tail dot get and increment modulus size. So tail dot get and increment means it is an atomic operation. So what it will do means first it will read the tail value, means it will get the tail value. That tail value will be stored in the slot, and after that it will increment the tail pointer by 1. So my slot index dot set. So slot value is initially 0. So first thread will be placed in the slot 0. If next thread comes, again we are incrementing this one, tail dot get and increment. So tail value will be, previously it is 1, right? So that 1 will be assigned to slot, and we are incrementing it to 2, like that. Now whenever first thread comes, so first thread comes, then what will happen is flag of 0 is true. So that particular thread directly enters into the critical section. Whenever second thread comes, so for that second thread, so we are assigning with false, so it will keep on spinning on this particular variable, right? So flag, how to release the lock? So in order to release the lock, what we are doing is flag of my slot index dot get. We are reading that particular state value equals to false. We are assigning it to false. And whatever the next thread is there, so we need to pass the lock to the next thread. So that we are doing by assigning it to the true. This is a simple and straightforward code. So here I'm using the lock. So so my system is capable of handling up to 12 threads. So I'm passing the 12 threads. Oh, sorry. So array lock with 12 threads. Java. So for counter, I'm passing. So we need to pass the 2 arguments. First argument is the number of threads, and second one is the time. So here I want to run it for 10 seconds. Sorry, it is counter test. So we need to pass number of threads and the time duration. So I want to run it for 10 seconds. So for 10 seconds, we are getting the throughput around 36.27752. And now let us increase it to 2 threads. Sorry, 2 threads. So always you need to remember one thing: if the size of the data structure is very less, and if you want to apply multiple threads, then automatically it will decrease the performance. So sometimes it will happen, sometimes it may not. Next, I want to execute for 4 threads. So here, say, if you look at the single threaded performance, we're getting the throughput around 36.2, and for 2 threads, we are getting the throughput 14.8. So it is decreasing. For 4 threads, it is decreasing. So we are getting 11. Now let us go with 8 threads. So for 8 threads, we're getting the throughput 8.96 MOPS, millions of operation per second. Now we'll go with the 12. Number of threads is 12. So for 12 threads, we are getting the throughput 0.02. It is completely decreasing, right? So why? Because here, if you look at the code counter program, so here we are using simple count variable, single count variable. On this count variable, we are applying 12 threads to increment that particular value. So it causes the contention on that particular variable. So every time it will increment first, first thread will increment the value, then it will pass the lock to the next thread, and then like that it is repeating. So because of that, we are getting the less performance. Next. Right. So any doubts regarding Anderson Q lock? Any doubts?
Hello, can you please explain like what is the like I was sorry, I was not able to follow. I was like doing something.
Yeah, tell me
Can
which
you
part?
just no? Can you just explain what is like happening? Just like just an overview, like what?
Okay, right. So previously, what will happen means, if you are going with task log or t-task or exponential backup, so all those logs works on a single variable, like it may be a locked variable or something else. So locked variable. Now, if all the threads are working on that particular variable, it causes the contention and it will cause the cache invalidations. So to avoid that particular problem, so what we are doing means, instead of using single variable, we are using the array of flags. So means here we are using the array. So we'll form a queue. Whenever a thread comes, that particular thread we are going to place in the first index, 0th index. When second thread comes, that we are placing in the first index. Then next thread will be placed in the consecutive indexes. Now here what will happen means, whenever first thread directly acquires the lock, then when first thread completes its execution, critical section operation, it will pass the lock to the next immediate thread. Next immediate thread will be the thread which is at index 1. So that thread will acquire the lock and it will complete its critical section and it will pass the lock to the next one. So like that, it will pass the lock to the next threads. Right. So here there is no concept of contention. Why? Because each thread spins on that particular index only. But when it comes to the task lock or t-task, what will happen? When a thread releases the lock, all the threads are trying to perform the get and set operation or test and set operation on that particular variable, which causes the contention. But here we are reducing that particular contention. Is it clear?
Yes, yes.
Okay, right.
So, but there is a what disadvantages that you are telling is that you have to.
Yeah, here the problem is, main problem is we should know the total number of threads ahead of time. And one more is, whatever the space is there, it is consuming the more space, right? So total space will be total number of threads, right?
Yes.
So if I want to use the 24 threads at a time, so I need to create an array with the 24 threads. So this space complexity is more. So yeah, tell me.
And just this flag array that you're saying, it will be stored in the like immediate cache like memory, right?
Yes. Yeah. So that is also one more problem, like I explained previously. So if it is storing in the same cache line, then what will happen means, it will cause the contention on that particular cache line. So to avoid that particular problem, what we are doing is, we are going with the concept of padding. So in padding, what will happen means, we are allocating one cache line per one particular thread.
Okay.
So this is also one of the problem, right? So to overcome these problems, we are going to the next lock.
Okay.
Is it clear?
Yes. And so like for a so between these two flags, like why like how does this solve your problem? I'm not understanding.
Right. See, if you look at this particular line, so on this line, there are 4 threads, right?
Yes, yes.
So if all these, like first thread will release the lock, and these remaining 3 threads continuously spinning on this particular cache line.
Yes.
So which causes the contention on that particular cache line.
But just now you said that like the 0th will be acquired by the first thread and the second will be acquired by the second thread and like this.
Yes, it will acquire, but it needs to spin on that particular variable, right?
Yes, yes.
So means when that particular thread knows that that particular thread acquired the lock, when this particular f is changed to true, right?
Yes.
That means it needs to continuously spin on that particular f only.
Yes.
So
To know the status.
to know the status. So every time it is spinning on a same cache line, if multiple threads are spinning on a cache line, it causes the contention.
Okay.
Okay, so to avoid that, what we are doing is we are going the concept of padding.
Okay.
Is it clear? Do you have any doubt?
And so like in the previous task log or t-test log, the contention was also occurring, but it was not like.
It is occurring on a single variable.
Oh, okay, okay.
Right. 1 minute. So I think you can see my screen, right?
Yes, yes.
Right. So if you look at this particular one, so all these variables are like first thread will enter into the critical section. Remaining variables are spinning on this particular variable only.
Okay, okay.
So here contention is more.
Okay.
Right. So this task lag problem can be overcome by using the t-task. So in t-test, what will happen means, so instead of continuously spinning on this particular locked variable, first these threads will read the lock status. If it is lock status is lock is busy, then these threads will get the cache copy. Then those threads will spin on that particular cache copy. Okay. Next, whenever lock becomes available, all these threads will try to perform the test and set operation on this particular lock. Again, it will cause the contention, right?
Yes.
So this is a problem. So like this, whatever the problems there in the previous lock, we are overcoming by using some other locks techniques. Okay, is it clear?
But now there is a contention for the like cache line.
Yes.
Okay.
Yes. And space is also more, right? It is
Yes.
consuming more space.
Yes, yes. Right.
So to
And
avoid,
just another question, like, why do we not know? Like, you are saying that the main problem in this Anderson lock is that the number of threads are not known beforehand. Like,
yes, we should know about the total number of threads.
but like, but people like when you are using a HPC, you know the number of threads, right? So like that's not a problem.
It's not like, for example, if you want, if you are building an application, again, if you want to deploy it in some other system, then again you need to know the number of threads and you need to do the modification in that particular code, right? If you look at this particular code, so here we are passing the number of threads to number of threads is 12, right? So
But
like that, every
okay.
time you need to do.
So, but like I am hard coding this here, right?
Yes, we need to do the hard coding.
But can I
Like,
do like
yes, we can do the soft coding by getting the total number of process available in the system and we can assign it, no problem.
yes.
Yeah, that one also we can do.
Okay.
Okay, fine.
Okay.
Right. Right. So then we can overcome those problems by using the concept of CLH lock. So CLH lock is also a Q lock. So it is based on the three scientists. One is Kerg, Hargerston, Landis. So C means Kerg, L means Landin, and Hagerston. H means Hagerston. So these are the three people. Now, here, when you look at the array lock or Anderson lock, it follows the FCFS order, first come, first serve order. So here CLH also follows the FCFS order. Whichever thread comes, that particular thread will be executed first. And here, whatever the size is there, size small and size of that particular size constraint size overhead per thread is also very small, right? Now here what will happen means, initially this tail is pointing to the false record. This is a false record and this is a tail. Now this particular thread is idle. Whenever any thread wants to enter into the critical section, it will create this is a qtail. Oh, sorry, this lock false. So here false indicates that lock is free. Next, whenever this particular pink thread wants to enter into the critical section, it will create an record. This is a QNode object. So it is creating a QNode object with the value true. Next, after that, what will happen means it will swap this particular value, means tail will point to the true, and this particular thread will spin on the false block. To acquire the lock, the thread sets the locked field value of its Q node to true, meaning is that that particular thread is ready to release the lock. Now, so I told you whatever the tail pointer is there, tail pointer will point to the thread and whatever the thread's Q node, and that particular thread is spinning on the predecessor Q node. Next, here another thread wants to acquire the lock, so it will do the same steps, means it will create a Q node. So here Q node value is true, and after that it needs to point the, means tail should point to the that particular red Q node. So here we are performing the swapping. So what it will do means, so this particular red thread will point to the pink thread Q node, and the tail will point to the true node, this red node. Is it clear? So simply, just I'm repeating one more time. So whenever new thread comes, so new thread will create its Q node, and Q node value is true, and it needs to swap tail pointer to its node, its Q node, and it will spin on the predecessor Q node. So here predecessor is pink thread Q node. So this red thread will spin on the pink thread Q node, and tail will point to the red thread Q node. Swapping, right? Now, so if you look at this particular one, it forms a linked list. Like it is not a direct linked list, it is an implicit linked list. Means it is forming like this. Now, next one. So it will spin on this particular field. So until this particular thread modifies this particular true to the false. So means it is not directly spinning on this particular thread location. Instead of that, it will get a cached copy, and it will spin on that particular value. Whenever this particular pink thread releases the lock, it updates its Q node value to false. So then this red thread will be notified saying that its record value is false, means that particular previous thread releases the lock. Now this red thread can acquire the lock, right? So here pink thread releases the lock, and now red thread will acquire the lock, right? Now, so if you look at this particular A lock, so total we require n number of locks. If you are, let us assume you are having n number of locks and sorry, L number of locks and n number of threads. Then total space usage is order of ln. But here in CLH lock, it will be order of L plus n. Right. So here, whatever this particular node is there, how to create that particular node. So here we are creating the node by using this particular atomic Boolean variable. So here locked field is a atomic Boolean. So initially we are initializing with the true. So indicating that not released at. Here is the code for the lock function. So initially we are using the atomic reference Q node. So here Q node is nothing but it will point to this particular Q node. Here in that particular Q node, we are having the one field called locked field. So here we are using the atomic reference tail. So here, what is this atomic reference? So this is a class in Java, which is available in the java.util.concurrent.atomic package. So which will provide a way to automatically update the reference to an object. So here we are declaring an atomic reference variable name tail that holds the references to the objects which is of type Q node. Next, so here we are creating the new queue node, which is used to create a new queue node. So which is local to that particular thread. Next, here whatever the swapping operation is there. So if you look at this particular case, whenever any thread comes, we need to create that particular queue node. After creating the queue node, then we need to get the predecessor, and we need to that particular new thread will spin on the predecessor, right? So that step we are doing here. So here what is happening? So get and set of my node. So this is an atomic operation, right? So get tail dot get means first it will read the tail object. So whatever the tail will point to some object, right? That object we are getting, and we are storing in the predecessor. And in the next step, we are setting the tail to the my node. Okay, right? So this is an atomic operation provided by the atomic reference. So it automatically gets the current value of the tail and sets it to the new value. That is my node. So the previous value of tail is written by this particular method. And after that, so we are maintaining the loop. So it will spin until the park.locked false. So here, predecessor dot locked. So whatever the pred.locked value is, we are assigning with the true, right? So true, that's why it will spin on this particular while loop. This is called a wait loop. So once the predecessor updates the locked value to false, then it will exit from this particular block. Next, here, when it comes to the unlock, it is simple. So here, this particular thread, my node dot lock dot set, we are setting it, updating it to the false. And here we are using this particular for in order to recycle that particular node. Right. Now, so what are the advantages with the CLH lock? So like a lock, this algorithm has each thread spin on it on a distinct location. So a lock also will spin on distinct location. Here also it will spin on distinct location. And when one thread releases the lock, it invalidates its successor cache only. And when it comes to the size, it is size is also very less. But the main problem with this particular CLH lock is doesn't work for uncached NUMA architectures. NUMA architecture means non-uniform memory access architecture. We'll see that particular point about this after program. Let us see the program. Yeah, for a single thread with the duration of 10 seconds, we are getting the throughput 36.5 MOPS. Let us go with the two threads. So when compared to the A-lock, we are getting the better throughput. For A-lock single threaded performance is 36.2 MOPS, but here we are getting 36.5 MOPS. For 11th, for two threads also, for if we look at the A-lock, two threads performance is 14.8 MOPS, but in CLH lock, we are getting 11.38. And here, when it comes to the four threads, so the performance is decreasing for CLH lock. Then let us go with the 8 threads. For 8 threads, we are getting the throughput 6.9 MOPS, but for A lock we are getting 8.9. And for single threaded performance, like whenever we are considering 12 threads. So if you look at the A-lock 12 threads performance, we are getting throughput 0.02 MOPS. But here in CLH lock, we are getting the throughput 0.12 MOPS. So better than the A-lock performance. Right. Now in CLH lock, the main problem is it doesn't work for uncached NUMA architectures. NUMA means non-uniform memory access. So if you look at this particular mission, so when a particular thread spinning on a local variable, memory will be very fast. But when a thread wants to spin on a remote location, then memory will be slow. So that is the main problem. So if you look at the CLH architecture, so each thread will spin on the predecessor location, right? So here, this particular, let us assume this particular last thread is spinning on its local cache, then it will be very fast. But if it is spinning on some other node, then every time it needs to go to that particular memory location and get the value, and it needs to perform the operation, right? So it will take certain amount of time. There will be communication cost as well as whatever the memory is there, like memory is also slow. So if the memory location is remote, then performance will suffer, right? So that is a problem with the NUMA architectures. Is it clear? Any doubts regarding the CLH lock? Is it clear? Do you have any doubts? Yeah, okay. Now, so here in NUMA architecture, in CLH lock, so CLH locks each thread spin on its predecessor location. So whenever you are applying CLH lock on NUMA missions, at that time it causes the problem. Why? Because if the particular thread is spinning on a local location, the memory will be fast. If it is spinning on a remote location, memory will be slow, right? So to overcome this particular problem, we are going with the concept of MCS lock. So MCS lock means Meller, Scrummy, and Scott lock. So this is also one of another kind of queue lock that ensures that process always spin on a fixed location. So this one works well for cache-less architectures also. Means instead of spinning on a remote location, it will spin on its local memory only. That is the main advantage with the MCS lock. And so it will take less constraint. Why? Because small and constraint size or constraint size overhead. All right. Now, so initially, if it is first thread, then a tail will be pointing to the null. Let us assume in this case, already some thread is in the critical section. Okay. Now this particular pink thread is initially idle. Whenever this particular thread wants to acquire the lock, so it will create a queue node. Now here, previously in CLH lock, queue node consists of only one field, that is locked field, right? So we are indicating with the true or false. But here in MCS queue node, it consists of two fields. So in MCS queue node consists of two fields. One is locked field and next will be the next field. So this locked field will store the true or false in order to indicate that whether the particular thread is acquired the lock or not. And the next field will point to the next queue node. So for that purpose, we are using the two fields. Now, whenever thread wants to acquire the lock, first it will create a queue node, allocate some memory. After that, what will happen means it will swap. It means whatever the tail pointer is there, tail pointer will point to the newly created queue node, and this false will point like whatever the previous queue node is there, that will be pointing to the new queue node. So that we are doing in a single step. So swap means what will happen means whatever this particular tail is there, tail will point to the last node, and whatever this particular no for like pink color queue node, sorry, green color queue node is there, that will be pointing to the pink color queue node. So this is a step, right? So now in this case, this particular pink node is pink thread is not spinning on the previous record. Instead of that, it is spinning on its own record, its own queue node. So that is the main advantage with the MCS lock. So if you look at the CLH architecture, in CLH lock, what it will do means it will each thread will spin on the predecessor node. But here in MCS, each thread will spin on its own queue node. So this is what we are doing here. Now, after that, so whenever it is pointing to this one, whenever new thread comes, so this particular pink color acquired the lock, and here we are doing that particular we are representing that particular notation. Then after that, this red color thread wants to acquire the lock. So whenever it wants to acquire the lock, it will create an queue node. So here it is creating a queue node. Now what it will do means, now this particular pink color queue node will point to the red color queue node, and this tail will point to the red color queue node. That we are doing here. So, right. So, right now, this red color is pointing to the next queue node, that is red color queue node, and tail will point to the last node. This is how lock acquire function works in the MCS lock. So it will spin on this particular true field. Now, whenever this particular thread wants to release the lock, so what it will so release the lock, it will update, means this particular queue node will update the next thread by changing its flag bit. Until that particular time, it will spin on that particular queue node only. Right. So if you look at this particular piece of code, here we are creating a queue node class. So here queue node class, we are declaring two variables. One is locked field, and one more is the next. So next will store the address of the next queue node. So which is of type. So that's why we are declaring the next of type queue node. And here we are declaring both the fields with the volatile. So volatile means, so next field should be volatile because JVM model is met, and whenever a JVM model is met and loops are not optimized by the JVM. So for that purpose, we are declaring the volatile. And here initially we are declaring the locked field with the false. So false, then next field will be the null. So this is the lock algorithm of MCS lock. So here how lock function will work. So this particular line, queue node of queue node equals to new queue node. So here what we are doing means we are creating a new node. This line queue node equals to new queue node creates a new instance of the queue node class and assign it to the variable queue node, right? So here, so whatever that particular tail is there, we are representing the tail with the null initially. And whenever any thread wants to acquire the lock, so it will create an queue node. So if you look at this particular code, here we are representing locked value to false and next will be null, right? So that's why we are creating a queue node with the initial value of locked field value is false, and the next it will be point to the null. Next. So what we are doing here, So here tail is separate. So tail is initially null. Now here we are checking the condition. So this line Q node pred equals to tail dot get and set of Q node. So get and set of Q node. This method provided by using the get atomic reference, it automatically gets the current value of the tail. So what is the current value of the tail? Tail is null, right? So initially tail is null. That null will be stored in the predecessor and sets the new value. So what is the new value here? Q node. So this Q node will be updated to like tail will be updated to the new Q node, right? So that's why here tail. So tail is null. That's why whatever the tail is there, now tail is pointing to the new Q node. So and it will acquire the lock. If it is the first thread, then it automatically acquires the lock and it will enter into the critical section. Now, what if Q is not empty? So means some threads already there in the now, if you look at this particular diagram, so here tail is pointing to the some Q node. So means one already some thread is in the critical section. Now at that time, we are performing the same operation for each and every thread. So Q node of predecessor is equal to tail dot get and set. So tail will return the previous thread. So here pink thread is the previous thread, and now tail will point updated to the next thread. That is next thread is nothing but red thread. Now here predecessor not equals to null. So predecessor is not equals to null. Here, yes, it is here tail is pointing to the pink thread. So it will return the pink thread. So predecessor is not equals to null. True. Then Q node dot locked equals to true. So whatever the Q node is, this particular red thread Q node previous, whenever it is creating at that time, it will be false. Now we are changing it to true. And predecessor dot next equals to Q node. We are updating the pointer, means predecessor pointer, we are updating it to the next thread. And after that, this particular red thread will spin on this particular locker field value. That is true. So until this particular pink thread updates the locker field value to false, it will keep on spinning on that particular memory location only. Right? Is it clear? Any doubts regarding MCS lock method? So is it clear? Any doubts? Right. Till now, we discussed the lock method of MCS lock. So here what we are doing is simply we are creating the Q node. So after creating the Q node, we are performing the get and set operation on the tail. So tail will get the means we'll get the tail pointing Q node that we are storing in the predecessor. In the next step, so we are setting the tail to the new Q node. After that, we are checking the predecessor is not equals to null or not. If the predecessor is null, then directly we can enter into the critical section because that is the first thread. If the predecessor is not equals to null, we are adding the new Q node predecessor next is equals to Q node. And it will spin on its Q node until that particular Q node becomes false. Right? So this is a simple lock functionality of MCS lock. Now, if the particular thread completes its critical section and it wants to release the lock, how to release the lock? So now in this case, purple wants to release the lock. So this particular thread updates its next field, its next thread field to true, true to false. And it will, whatever this particular Q node, purple Q node will next pointer will point to the null. That is what we are doing here. So first step is this particular purple thread will update the next field locked value to false and its Q node next to the null. So this is what we are doing here. So after that, it will, sorry. Yeah. So here it is updating to false. Then this particular red thread acquires the lock and it will enter into the critical section. This is what we are doing. Now, this is the unlock method of MCSQ lock. Here, first what we are doing is we are checking qnode.next equals to null. Means we are checking that is there any node after the current node. If there is a node, then we can pass the lock to the next thread. If there is no Q node. So then what we are doing is we are performing the CAS operation, compare and set operation. Here tail dot compare and set of Q node comma null. So if there is no Q node, then we return. So here what it will do means it checks if the current value of the tail equals to Q node, means if the Q node is pointing to current Q node, then it indicates that is the last thread in that particular queue. So that's why we are checking what this tail dot compare and set of Q node comma null is doing is it checks if the current value of the tail is equals to Q node. If it is, the value of the tail is updated to null. The operator returns true if the comparison and update is succeed. Otherwise, it will return false. So that is what we are doing here is. So tail dot cas of Q node comma null. If tail is pointing to the Q node, then we are updating the tail to the null. And after that, we are returning. For example, if this particular condition is CAS operation is failure, so it will return false, right? So whenever it is failure, then what will happen means it indicates that there is some other thread in the queue. Then what we are doing is we are waiting until that particular thread comes. So while q node dot next equals to null, then if q node dot next equals to null indicates that we are waiting for other thread. Next, after that, for example, if this particular first condition itself is false, indicates that q node dot next equals to null. If this condition is false, means there is one more q node in the queue. So then we're directly going to the q node dot next dot lock equals to false. So what it is doing is, let us assume here this purple thread wants to release the lock, and this particular red thread wants to acquire the lock. So what it is doing means now purple thread release the lock by updating the next thread locked field value to false. That is what we are doing is q node dot next. So current q node is purple thread. So this purple thread q node dot next means it is pointing to the next thread, that is red thread. Now we are changing the red thread locked field value to false. It means this purple thread releases the lock and red thread acquired the lock and it will enter into the critical section. Right? So is it clear? Is there any doubts regarding MCS lock and unlock methods? Yeah, if no more doubts, then I'll go to the coding part. So whenever we are using the MCS lock on that particular counter variable, and if we are using only one thread, we are getting the throughput 55.0 MOPS. So if you look at the CLH lock, or if you look at the
Sir, excuse me.
yes, tell me.
Sir, your slides are, sir, like the code is not visible. I'm still seeing your slides.
Oh, sorry. I hope now you can see the screen, right? Right. Now, if you look at the single threaded performance of A lock, we're getting throughput around 36.2 MOPS, and for CLH lock, we're getting 36.5. But if you look at the performance of MCS lock on single threaded, we're getting 55.0 MOPS, and for two threads, we're getting 9.8. But here for A lock and CLH lock is giving the better performance. And if you look at the when number of threads is 4, the throughput of MCS lock is 9.6 MOPS, and CLH lock is 8.0 MOPS, and for A lock we are getting the throughput around 11.0 MOPS. Now for 8 threads, MCS lock is giving throughput 8.2 MOPS. CLH is giving 6.9 MOPS performance, and A lock is giving 8.9. So, but for 8 threads, MCS lock is giving less performance. But if you look at the 12 threads, so we are getting the throughput around 0.02. But if you look at the CLH lock is giving the better performance when compared to the both A lock and MCS lock. So here MCS lock is giving less performance than the AL lock, right? So this means all these locks we are applying on a single counter variable, but this performance may vary with respect to the application. Okay, so if we are increasing the size also, means here we are considering the duration as 10 seconds. So instead of 10 seconds, if you are decreasing it, the performance will vary. If you are increasing it to more, then it will vary the performance. And instead of single counter variable, if you are working on a data structures like trees, linked list, skip list, the performance will vary with respect to the with respect to the architecture as well as some other properties. We'll discuss that later. Now, this is how we're getting the performance. Now, if you look at the, now tell me, so is there any disadvantage with this MCS lock? So when compared to the CLH lock, MCS lock is better in instead of spinning on the predecessor in CLH lock, MCS lock spinning on its own Q node. So the like there is a advantage. Now, is there any advantage with this lock? So when compared to the all other locks, it is having some advantages, right? So it will spin on its predecessor, its own local Q node only, and it supports the new architecture also. So why? Because it's spinning on its own Q node, so it will be fast. So is there any disadvantage? Anyone? Right. Now, if you look at the MCS lock, so MCS lock gives the provides fairness in the sense whichever thread comes first, that will be that will acquire the lock first. Means lock fairness is FCFS, and MCS lock is a NUMA aware lock. And what is the problem is a good fit with NUMA and cache coherent NUMA missions. That is the main thing. Now, if you look at this particular NUMA mission, so here this particular NUMA mission is having two NUMA nodes, the NUMA node 1 and NUMA node 2, and each with 8 process. So NUMA node 1 is having 8 process, and NUMA node 2 is also having the 8 processors, right? Now, so here let us assume we are using the MCS lock to acquire the in order to enter into the critical section, right? So here what will happen means, as thread from different nodes access the data structure in the critical section, these locations bounce around the mission. Means, for example, first this particular thread wants to enter into the critical section. So then what will happen means, so it will access the critical section and it will perform the operation. Then after that, next thread will acquire the lock from NUMA node 2, then it will be entering into the critical section. After that, it will go to some other memory location and it will access that particular memory location and performs the operation. All right. Now, what will happen means, whatever the cache memory is there, like it will be means whenever node 1 is node 1 thread is accessing, then these thread will be store the cache memory, right? So whatever the content is there, that will be stored here. But whenever these particular threads wants to access, at that time again cache will be replaced with these threads information. And one more is, whenever this particular thread wants to acquire the lock, this will acquire the lock and it will process. Then after it is releasing, that means node 1 thread release the lock, then lock will be, if the lock is passing to the node 2, then what will happen means, this node 2 again will acquire the lock and it will come back. Again, if you are passing the lock to the node 1 thread, then like that, if you are transferring the locks to the node 1 thread first, then node 2, then node 1, like that, vice versa, then there will be a communication cost. So to avoid that particular problem, we are going with the concept of NUMA aware locks, or sometimes we are also calling this hierarchical locks. So in hierarchical locks, what is the main problem with the MCS lock means, MCS lock supports the NUMA architecture. Why? Because it will spin on its local node, local cache memory only. But if you look at the NUMA missions with multiple nodes, at that time, if the threads from the same NUMA node can access easily, but if the thread is spinning on a remote memory node, then the communication cost is more, right? And the memory, local memory is faster, and global, whatever the remote memory is there, it will be slower. So if it is, that is a problem, right? So let us go with the different locks. So just I'm giving the overview about other locks, hierarchical locks. So this till this slide, we are closing the Q locks. So this is the end of the Q locks. Now we are going with the next lock, that is hierarchical backup lock. So just I'm giving the overview about these hierarchical locks. So hierarchical backup lock. So whatever the previous backup lock is there, in backup lock, what we are doing, all the threads are trying to acquire the lock. At that time, if it is succeed, it will enter into the critical section, right? If it is failure, then we are sending back to waiting period for certain amount of time. If it is again after that time, after that particular waiting period, it will retry to acquire the lock. If it is failure, again we are sending that particular, means whatever the waiting duration is there, we are increasing it by twice. All right. So this is what happening. Now, what is hierarchical backup lock is, here, if my mission NUMA mission is having two nodes, this is a first node and this is a second node. Now what we are doing is, whenever both the threads are trying to acquire the global lock. So once the particular NUMA node thread acquires the lock, then if the some other thread comes from the same NUMA node, we are giving sending that particular thread to waiting period with less duration. If thread from some other node comes, then we are sending that particular thread to waiting period with remote backoff. Means whatever the local backoff is there, we are maintaining the local backoff as less, and when it comes to the remote node backoff, then we are providing the more backoff time. Means let us assume here start minimum backoff is 32 means, then here we are going with the minimum back for remote threads, we are going with the minimum backoff time is 1024, or you can vary with respect to the missions, you can change that. So that is what the hierarchical backoff lock means. If one NUMA node thread acquires the lock, for all other threads from the same NUMA node will be having less backoff time. If it is from, if the thread from the remote node, then it is having more backoff time. Right? This is how we are implementing the hierarchical backoff lock. And then next comes to the hierarchical CLH lock. So here hierarchical CLH lock also, which is similar to the CLH lock, but here if it depends on the number of queue nodes. If the number of queue nodes is 2, then we are maintaining the 2 queues. So this is a local queue. This is the first local queue, and this is the second local queue. So if the threads from the same NUMA node will form a one queue, and threads from the other NUMA node will form a queue. Now here we are maintaining the global tail. So both the local queues will be merged into a single one, and this will be processed, right? This is a hierarchical CLH lock. Next, one more concept is lock cohorting. So lock cohorting means, so here this lock cohorting can be implemented by using all the spin locks as well as queue locks. Means it is a combination of 2 or more locks, or we can say that it is a combination of 2 locks, at most 2 locks. Means for local lock, we can use the task lock. For this local lock also, we can use the task lock. Global lock also, we can use the task lock. Or we can use, for local locks, we can use the task lock, and for global lock, we can use the MCS lock. Or here in local lock, we can use the CLH lock, and in global lock, we can use some other lock also. Means lock cohorting is a combination of 2 locks. Now, what will happen? What is the concept behind lock cohorting? So in lock cohorting, so first any thread wants to enter into the critical section, it needs to acquire the local lock first. So here it acquires the local lock first. So after acquiring the local lock, this thread is trying to acquire the global lock. If it is succeed in acquiring the global lock, then what will happen means it will enter into the critical section, and it will perform its job, and it will exit from the critical section. Now, after exiting the critical section, instead of releasing the global lock, it will go to the local lock, and it will release the local lock. Once that particular local lock is released, then other threads from the same NUMA node can acquire the local lock. Whichever thread acquires the local lock, that particular thread directly enters into the critical section. Why? Because whatever the previous thread is there, it releases the only local lock only. It is not releasing the global lock. So other thread can directly enter into the critical section. And after that, this particular thread checks whether the cohort is non-empty or not. If it is non-empty, then it will go to the local lock, and it will release the local lock. Once it releases the local lock, then what will happen means other thread from the same NUMA node can acquire the local lock and enters into the critical section. Right? So it enters into the critical section. So once it enters into the critical section, after completion of its critical section operations, then it will release the lock. So it will, before releasing the lock, it will check that whether the local cohort is empty or not. So in this case, this particular first NUMA node is empty. So that means empty cohort. So it will release the global lock, and it will release the local lock also. And once it releases the local lock and global lock, other threads from other NUMA nodes can acquire the local lock. After acquiring the local lock, then it can go to the global lock and it can acquire the lock, global lock. So once it's complete its critical section, then it will release the lock. Before releasing the lock, it will check whether the cohort is empty or not. If it is empty, it will release the local lock, global lock. Otherwise, it will release the local lock. Right. So here it is releasing, entering, and that's it. So it will continue like this. Now, what will happen means, so these threads will access the local lock, like local threads from the same pneumo node will acquire the lock. Then after that, it will pass the lock to the remote lock. So then what will happen means, whatever the communication cost between the threads from different nodes will be reduced in this lock cohorting. So after lock cohorting, we are having different locks like CNA lock, shuffle lock, hierarchical MCS lock. Like that, we are having different locks. So we are having different locks. Now, now the question is, one lock to rule them all. Right. So in this session, we saw different types of spin locks. In the previous session, we discussed about spin locks, and in this session, we discussed about Q locks. So all these locks vary in characteristics and performance. Right. Now the question is, we are having different locks. Now, which lock is better? Means we discussed about TAS, TTAS, TTAS with backoff, A lock, CLH lock, and MCS lock. So each better than others in some way, but there is no one solution. Means if I want to use some synchronization mechanism in my application, which lock I should use? Either I should use a TAS lock or TTAS or some other locks. Which lock? So there is no solution for that. And lock we pick really depends on three things. One is the application, which application you want to on which application you want to use that particular lock, and the hardware. If you are using the NUMA hardware, at the time, if you want to use TAS or TTAS, TTAS with backoff or A lock or CLH, you can use these locks, but the performance is less when compared to the MCS or other locks. And which properties are important? We need to consider those one also. Like if you look at the first three locks, means whatever the spin locks are there. So spin locks are not following the FCFS order. Means FCFS means first come first serve order. If highest priority thread comes, then whatever the lowest priority thread is there, it will be in the waiting state only, which leads to the starvation, and then it leads to the deadlock also. So at that time, so if you want to use the FCFS in your application, so at that time, if you want to use the TAS lock or TTAS or TTAS with backoff, you won't get any performance. But if you want to use the if you want to follow the FCFS order, then you can go with the A lock, CLH lock, or MCS lock. You can go with any lock. Right? So is it clear?